Hello guys, welcome once more to another live session here on YouTube on the Mathematics Academy for Africa YouTube channel. So here we are going to be looking at pure math with mechanics paper 3, equation on center of mass. The equation reads, figure 1 is a uniform square lamina ABCD of side 6A. C1 and C2 are circular portions of the lamina each of radius A. The side AB of the lamina is tangent to C1 at its midpoint E, while the side AD of the lamina is tangent to C2 at its midpoint F. The portions C1 and C2 are removed from the lamina. Find the distance from DC and from BC of the centroid of the remainder of the lamina. Hence, show that if theta is the angle of inclination of BC to the vertical when the remainder of the lamina is suspended freely from C, then tangent of theta is equal to 1. Alright, so we are live once more on YouTube. If you are joining us for the first time, endeavor to hit the subscribe button. You share the video with you share the live session with your friends. You subscribe to the channel, you comment, and you also turn on your notifications so that whenever subsequent live sessions are available, you'll be notified to come and follow. Okay, if you have a problem, the comment section is open for you to table your problem. I'm going to give my number at the end so you can get to me in case of a difficulty. Okay, so I'm going to be very brief and detailed in this live session. So we are looking at center of mass. We have a diagram given to us, and the diagram has basically been described to us. So we have a square lamina whose side is 6A. E is the midpoint of the side AB, and F is the midpoint of the side AD. C2 is tangent to the side AD at the midpoint F, and C1 is tangent to the side AB at the midpoint E. The radius of C2 is small a, and the radius of C1 is also small a. They have equal radii, which is A. Alright, so we need to find now the portions C1, C2 and C1 are actually removed. Now we need to find the distance from the side DC and from the side BC of the center of mass of the remaining lamina when the portions C1 and C2 are removed. Then later, if we suspend the lamina at the point C and it hangs freely in equilibrium, we need to show that the tangent of the angle of inclination between BC and the vertical is actually equal to 1. That's the tangent of the angle. Okay, so basically we are going to create a table where we are going to divide the lamina into different portions. We determine the weight of those portions, then we take moment about the axis we are finding the center of mass from, or the distance of the center of mass from. Okay, then later we do the suspension. So what we are going to do is that if we want to take moment, you know that moment is the mass times, the weight, or the force times the perpendicular distance from the axis. But if we consider every portion here, these portions don't have masses. Okay, so we are going to let lambda be, so lambda be the mass per unit, the mass per unit area of every portion taken. What does this mean? This means that lambda is the mass of a portion over the area of the portion. So with this, we can be able to get a mass of a portion. It's going to be the mass per unit area times the area. This helps us to get the weight because the weight is mg. So the weight of a portion, which is mg, becomes lambda a times g. So all we need to find is the area of the portion, because g is the acceleration due to gravity is constant. Lambda is also constant for all the portions. Okay, now so we are going to create a table. So we create a table of values. We create a table. So we have the portion, we have the area of the portion, we have the weight of the portion, then we have the distance of the center of mass of the portion from the various from BC and from DC. Okay, so let me just do this. So we have portion is the first thing, then area of portion, then weight of portion, then distance of center of gravity of the portion from, so the distance of the center of gravity of the portion from, first things first, we need to find the distance. Let me try to put two columns here. Okay, so we are going to find the distance of the center of mass of the portion from BC, okay, from BC and from DC, according to what the equation is saying, from BC and from DC. Okay, so I think we just have to send these guys down here. Voila. Okay, so let's come back to our diagram. So the first portion we can take is the whole lamina, okay, the portion A, B, C, D. All right, that's our first portion. So our first portion is a portion A, B, C, D. What is the area? It's length times width. In fact, it's a square, so it's the side. It is the side squared. The side was given to us as 6A. So the area is going to be 36A squared when you multiply 6A with 6A. So you have 36A squared. Okay, 36A squared. Oh, sorry about the 36A squared. What is the weight? It is lambda AG. So you are going to have 36 lambda A squared G, or 36A squared lambda G, any of them. Now, what is the distance of the center of mass from BC? So it's very important that we go to the diagram and we try to indicate its position. So the center of mass will lie at the center because it is a square, so it lies at the center. Okay, so since it lies at the center, what is the distance? What is the distance of that point from BC? So what is the distance from BC? Is the side to the left. So we need to find this distance. What is this distance? It's just half of the length or half of the side. Okay, because it's the center, so it's going to give us 3A. Okay, it's going to give us 3A. So it actually depends. Let us just try to indicate our axis, okay, so that we know exactly if it's going to be negative or positive. So what I'm going to do is that I'm going to come to this diagram and indicate my axis. So that's a vertical axis. Okay, that's a vertical axis. That's my vertical axis. Okay, and then my horizontal axis is DC. So this is my horizontal axis here. So here is my horizontal axis. So that's my vertical axis and this is my horizontal axis. Okay, okay. Now the next thing we do is that, okay, if that is the case, it therefore means that this point C here is like the origin. Okay, this point C is like the origin. So any distance to the left is negative, any distance to the right, in fact any distance to the left is negative, and any distance below is also negative, because if this is the origin here, anything to the left is negative. Okay, so now let us go and indicate the center of mass of the figure. So the center of mass of the square is lying at the center. So let's just pick that this is the center. Now, what is its displacement from the BC? Is a horizontal distance, which is actually 3A. But since it is lying to the left of BC, it is now negative 3A. I don't know if you guys are getting. If it was lying to the right, it's going to be positive 3A. So if you want to calibrate, you realize that this is actually going to be negative 3A. Like if you want to calibrate it, okay, if you want to do a calibration on the horizontal axis there, then this guy here is actually going to be negative 3A. All right, so this man is actually going to be negative 3A. Why is it so? It is because this point C here is at 0. Okay, the point C there is actually at 0. So if the point C is at 0 and we are moving to the left, it therefore means that that guy there is negative 3A. So negative 3A. Okay, now what is the distance from DC? Because we also need the vertical distance. What's the distance from DC? The distance from DC is this vertical distance here. Okay, this vertical distance, and this vertical distance is also negative 3a, because if you're calibrating on the y-axis, you realize that if you calibrate on the y-axis, this will be negative 3, all right, because this is 0. This at the point B here, it is at negative 6, all right, because you are going downwards. So at that point, at the point B, there is at minus 6. So this minus 6 down here. Okay, so since this is the center, this minus 3. Then at the point D, at this point D is also at minus 6. So the point D, it is also at minus 6. Okay, so that is it. So the distance of the center of mass of the ABCD from the side BC is negative 3a. Okay, remember we are taking the negative sign because actually displacement, negative 3a. What about from DC? From DC is also negative 3a. Okay, next thing is, let's take the circular portions. So let's take the portion C1. Okay, then we also have the portion C2, and then we actually have now a remainder, because when we remove those portions, you are going to have a remainder. So what is the area of C1? Is pi radius squared. So we have pi, the radius is a, so pi a squared. So its weight is going to be pi a squared lambda g. Okay, pi a squared lambda g. So let me just try to put the a squared first so that everything is uniform. So 36 a squared lambda g. Now what is the, let's just feel this radius here is also pi a squared. So its weight is also pi a squared lambda g. Okay, now for the remainder, what is the area of the remainder? It is the area of the whole minus the area of what is removed. Okay, because the whole lamina here contains the C1, C2, and then the remaining part when C1 and C2 are removed. So we are going to have 36 a squared minus a squared, sorry, minus pi a squared, then minus pi a squared again, so it's minus 2 pi a squared. So that is it. So we need to sum everything here. Then we take 36 minus what is removed minus what is removed. So we have all of this. So what is going to be the weight? It is going to be the area times lambda g. Okay, so we have the area times lambda g. So that is it. Okay, so let's now focus on the distance of the center of mass of those portions from the axis given to us. Let's try to focus on the distance of the center of mass from the axis. Okay, so let us go to C1. So we go to the diagram. I'm going to remove all of these things. Let me just try to shift them to one corner. Okay, now where is the center of C1 lies at its center. Okay, so the center of C1 will lie at the center. Maybe this is the center. Here's the center of C1. So the distance of the center of mass the distance of the center of mass of this C1 from BC is this distance here, this distance. Okay, and this distance is basically negative 3a. Why are we saying that? Because this point E here is a midpoint of AB. Okay, and since it's the midpoint, it therefore means that if I draw a line, let us try to indicate the original center of the whole figure was here. Okay, and if the point E is a midpoint of AB, it therefore means that if we draw a line passing through E, is going to pass through the center of mass. All right, it therefore means that you realize that this center here and the center of C1 are on the same line. Therefore, they will have the same distance from BC. Are we getting? So the distance is also negative 3a. Now, what about the distance from DC? So the distance from BC is minus 3a. What about the distance from DC? So we now need the vertical distance. So we need the distance from the center. Okay, the distance from the center right up till DC. So we need this vertical distance. Okay, we actually need that vertical distance. So how do we get that vertical distance? So we need that vertical distance. Let me just give it. Let me put in red. Okay, we need that vertical distance. Okay, how do I get that vertical distance? Now we actually know that, so let me just try to remove, let me shift this one to one corner. Let me remove this man as well. Let me also remove this center. Voila. So we need this vertical distance here. The distance from the center of mass of C1 to DC is going to be negative because it is below DC. Okay, now what is the distance? We know that the radius of C1 is small a. What does this mean? This just means that if I draw a little line, that is, if I draw a little line passing through the center, okay, the distance from AB to here is small a. So this distance here is small a. Okay, so since the whole distance here is actually equal to 6a, it therefore means that the remaining distance here is 5a, but since it is below, it is now negative 5a. So if you want to try to put a demarcation, if you want to put a little calibration, it means that this point here, right, this point here is minus 5a. Okay, so this point here is at minus 5a. It's at 5a from the top, which is minus 5a since it's below the top. So because this little distance down here is a, you just realize that if I move from minus 5a to minus 6a, I've just added negative a because I'm moving downwards. All right, so the distance from the center right up till DC will be what? Minus 5a. If we're finding the distance from the center to AB, is just going to be positive a, because if our axis was horizontally down here, then all distances above it are positive. Okay, but since the axis is right up here, then any distance below it is negative. That's a displacement. So this from here to here will be minus 5a. all right. Okay, so I come to my table and I replace it with minus 5a. Now let's go to C2. So we are shifting. So to C2, we are going to also indicate this is the center of C2. All right, here's the center of C2. Okay, now next thing, what is the distance of the center of mass of C2 from BC? So the distance of the center of mass of C2 from BC is this distance, the distance from this center of mass, okay, right up till BC. This horizontal distance here is what we are looking for. Okay, we need that distance. So how do I get that distance? Now the first thing is that I know that this vertical line that is here, okay, I know that okay, if I put a vertical line here, let me just try to put a vertical line. Okay, now this short distance, let me try to carry this guy to that portion. So this little distance here is the radius. Are we there? This distance here is the radius, of it, which is small a. Okay, so it therefore means that this remaining distance here is going to be 5a, because the total length is 6a. We need the distance from the center of mass to BC. Okay, so this distance here is going to be 5a, but since it is to the left of BC, it is negative 5. So if we want to maybe do a calibration, right, if we want to do a calibration on the x-axis, that is going to be minus 5a. all right, so instead of having 5a there, instead of having 5a, is going to be minus 5a. So this man here is minus 5a, this man here is normally minus 6a, so this man is minus 5a. So the distance from this center to BC is minus 5a because it is to the left. Are we getting? So I come here and put minus 5a. Now what about the distance from DC? Now the distance from DC is now this vertical distance here. Okay, this vertical distance from the center right up till where DC is. So the distance from DC is that vertical distance. So let's also try to get it. So we are going to apply the same principle we have applied already. Okay, so we need now the vertical distance. So the distance from the center of mass, let me try to reduce so that we get, voila. So we need the distance from this center to DC. all right. Okay, so how do we do to get that distance? Now we know that C2 is tangent to the side AD at the midpoint. Now the original center of my ABCD is here. Since it is tangent at the midpoint, it means that if I draw a line, you see this line here, this line that is passing through the center will normally pass. If I draw a line through F, right, it's going to pass through the center. The line is not really straight. So if I draw a line through F, it must pass through the center of my circle, and automatically also passes through the center of the whole plane. Okay, so with that said, we need the distance. Which distance do we need? We need this vertical distance here. We need this vertical distance here. Okay, so to get this vertical distance, I know that this vertical distance down here, that is, I know that this distance, the distance from the center right down here, is just half of the length of the rod. Sorry, half of the length of the square lamina. Okay, because that is the center. Because this distance here is the same as this other distance here. Okay, and this other distance here is just 3a, actually negative 3a, because it is below. Okay, so since we need this distance in red, that is the distance from here going up, it's also going to be, in fact, from here you clearly see that it is at minus 3a. Okay, so it's at minus 3a. If you check very well, the distance from its center right up here is at minus 3a. So I come here and I put minus 3a. Voila. So we are basically done. So now when I remove these portions, when I remove this man and I remove this man, I'll be left with a lamina whose center of mass will be at the certain point. Now the distance from BC, the distance of the center of mass of that guy from BC, right, will be maybe let me just try to clear the figure so that we really see, we try to indicate the new center of mass of the remaining lamina. Okay, the center of mass of the remaining lamina. So the center of mass of the remaining lamina, maybe let me just say, when I remove those portions, it can lie maybe somewhere up here. Okay, now we need the distance from BC is this horizontal distance. All right, so see, it is negative, so we are going to say negative x bar. No, let's just say x bar. Let's just say x bar, because the distance from BC, so x bar, we don't know it, we are going to find it. Now the other one is going to be y bar, we don't know, we are going to find. Okay, so the distance from BC is a horizontal distance, we call it x bar. The distance from DC is a vertical distance, we call it y bar. We need to find x bar and y bar, and finding it, we basically have to take moments about those axes. Okay, so this is actually the first step in doing. If you miss this step, everything you're going to do is not going to make sense. All right, so that's why I'm taking my time to explain. So I filled my table. The next thing is, now we are going to take moments about the various axes. So take moment first of all about BC. Okay, about BC. So if you take moments about BC, we are going to take the moments of the individual portions that make up the whole body. The individual portions are C1, C2, and the remainder, because the remainder is still inside the whole body. They will equate it to the moments of the whole body about BC. So what is the moment of C1 about BC? It is the weight of C1 times its perpendicular distance from BC, which is just minus 3a. Okay, because C1, the perpendicular distance from BC was a horizontal distance, which is what we filled in the table. So the moment of C1 will be the weight of C1, which is this. We multiply it with the perpendicular distance, and the perpendicular distance is negative 3a. Then plus, what about the moment of C2? Is also the weight times its own perpendicular distance, which is minus 5a. Then plus, what is the moment of the remainder? It is also its weight. Okay, it is also its weight times its own perpendicular distance, which is x bar, we don't know. Then we equate it to the moment of the whole body, which is the weight of the whole body. The weight of the whole body, we multiply it with its perpendicular distance, which is negative 3a. So from here we make x bar the subject of the formula. So let us simplify term wise. So the first, in fact, I think we can see a squared lambda g. Is a squared lambda g common everywhere? Yes, it is common everywhere. So this a squared lambda g, I'm just going to put in red. cancels with this a squared lambda g, okay, cancels with, now you see that we can factorize a squared from here. If I factorize a squared from here and also factorize a squared from here, I'm going to have a squared outside here. So the a squared lambda g also cancels here, okay, and then the a squared lambda g also cancels. So we are going to be left with pi times negative 3a. This also what? Negative 3a times pi, okay. So we are done with the first term. Now let's go to the second term. We are going to have 5 times negative 5. Pi times negative 5a is negative 5a times pi. We are done with the second term. Let's go to the third term. So we are going to have in the third term there is x bar, and we'll be multiplying it with 36 minus 2 pi, okay. Then we equate it to, on the right hand side, 36 is going to give us 36 times negative 3a. Then we try to simplify by making x bar the subject of the formula. So here we have negative 8 pi a, so negative 8 pi a plus, let me just copy this x bar times that quantity. Then I equate it to 36 times negative 3a, okay. Now from there, let me just copy what is here so that we go directly to the next page. Okay, so this is what we have. So from here, what do? I need to find x bar. So x bar times 36 minus 2 pi will be equal to, now what is 36 times 3? 36 times 3, sorry, 36 times negative 3, yes, we need to also consider the negative sign. Then we later make x bar the subject of the formula. So if you do 36 times negative 3, okay, 36 times 3, 108. So minus 108a. Then we need to add this man on both sides, okay. So plus 8 pi a. Then we now divide both sides by the coefficient of x bar. So x bar will be equal to, the numerator is a is common, okay. I think if we take, let's just see if, anyways, let's just put 8, no, a is common, so you have here 8 pi minus 108 divided by 36 minus 2 pi. Okay, so what do we have at the end of the day? At the end of the day, from the denominator 2 is common, so I can take a over 2. Now the denominator becomes 18 minus pi, okay. The numerator, I think, let's see, is 8 common. What is 108 divided by 8? Can it go? 108 divided by 8 cannot go. So divided by 4 it can go. So 4 is common. So if I factorize 4 from the numerator, 4 from 8, you actually be left with 2 pi. Then 4 from 108, you'll be left with 27. Okay. So at the end of the day, therefore x bar is equal to, now denominator is 18 minus pi, okay. Numerator, we see that 4 over 2 is 2, so I'm just going to put 2 outside. In fact, let me just multiply all through by the 2. 2 times 2 pi is 4 pi, then minus 2 times 27 is 54. Then we multiply the answer by a. Okay, now if you punch, you realize that this result is negative. Just to tell you that actually it is negative because it is to the left of the axis. Okay, so clearly it has to be negative. All right, so my x bar is actually negative, which is perfectly okay. All right, now let us take moments. So we are going to take moments again. So I'm just going to copy the table and paste here so that we don't move forth and back. So we are going to now take moments about DC. then we now get y bar. Then we now move to the second part of the equation. So let's take moments. So here's my table. We are now going to take moments about DC. Okay, if we take moments about DC, same story. We take the individual portions. We have the weight of C1. We multiply it with its perpendicular distance from DC, which is minus 5a, plus the weight of C2 times its own perpendicular distance, which is minus 3a, plus the weight of the remainder, okay, times its own perpendicular distance, which is y bar, equal to the weight of the whole system, that's the weight of the whole lamina, which is this, times its own perpendicular distance, which is minus 3a. Okay, now simplification starts once more. So this implies that, first things first, a squared lambda g, we put it in red, it cancels with a squared lambda g here. Now here we can factorize a squared, okay, so that we have an a squared lambda g as a factor, which later on cancels, and this man also cancels. Okay, so here we are going to be left with negative 5a pi minus 3a pi is negative 8a pi. Now we are done with the first two terms. Okay, now let's come here. We have plus y bar times 36 minus 2 pi equal to same story. When you do 36 times this, I think we had negative 108a. Okay, then we now get y bar directly. So y bar is going to give us, now first of all we need to, let's first of all add 8a on both sides. So if you add 8 pi a on both sides, we have everything here to be equal to negative 108a plus 8 pi a. Okay, so we are going to divide both sides by 36 minus 2 pi. Then up here is going to be 8 pi a minus 108a. Okay, that's what we have. Okay, wait, it's not the same thing. It's like it's the same thing here. It seems like it is the same thing. Anyway, it's no problem. All right, so next thing, what do? We are going to have what do we have? It's practically the same thing, okay, because I think that is what we have here. We perfectly have the same thing, so no problem. X bar equal to y bar, so there's no need to be simplifying again, so I'll just copy and paste. So therefore means that, therefore my y bar is equal to this. So you can notice that x bar is equal to y bar. All right, so we have successfully gotten the distance of the center of mass of the remainder from the bounding from the side lengths, which is BC and DC. Okay, I've gotten it. Okay, now second question. Hence, show that if theta is an angle of inclination of BC to the vertical when the remainder of the lamina is suspended freely from C, then tan theta is equal to 1. We need to show it. So I'll just have to copy this diagram so that we go below and try to do the suspension. My word is not responding, so you guys should just give me, okay, it's back. Okay, so when there is suspension, so let us try to imagine that I try to suspend this body, that is the remainder. Okay, I try to suspend the remainder of the lamina at the point C. So I try to suspend at the point C. That's my point of suspension. So let me indicate that I am suspending at the point C. Okay, so if I suspend at the point C, how will this body move? In which direction will the body move to? Is it going to move up? Is it going to move up, or it is going to move down? That's the question. So if I suspend at this point, okay, if I suspend at the point C, does the body moves up or it actually moves down? It basically moves down, right? Because if you suspend here, it cannot move up. It's going to move down. So maybe let's just say that, okay, when it is suspended, we have something like, because it hangs freely, okay, so let's just say that this is the new position. Now what you have to note is that, let us say that, okay, initially the center of mass of the body, oh, my word is not responding again. Anyways, let us, oh, I copied the whole diagram. Wait, let me put the original. Let us say that initially, wait, here's the center, there's the position of the center of mass of the remainder. Okay, let's just put that is the position of the center of mass of the remainder. So what happens now is that we now suspend at the point C so that it hangs freely in equilibrium. So if you suspend at the point C, you have a tendency, it cannot move up like this. It's impossible. It's impossible for it to move up. So if I suspend at the point C, it's going to kind of fall down. Okay. So the principle is that the line, okay, the line that is joining, so the line that is joining the point of suspension and the line that is joining the point of suspension and the center of mass of the body is the vertical. Okay, so when they are talking about the vertical, then the vertical is actually the line joining the point of suspension C and the center of mass of the body. Let me try to make it, let it be, yeah, be kind of vertical. So this is it. So the line joining the center of mass of the body and the point of suspension is the vertical. Alright, it's a vertical. So this line like this is purely vertical. Not purely vertical, but it's a vertical. Anyways, so this line is a vertical. Okay. Now you see that the question asks us to show that if theta is the angle of inclination of BC to the vertical. So where is BC? This is my BC, okay? And where is the vertical? This is my vertical. So the angle is the angle between this guy here. In fact, let us indicate that. Let us say the center of mass is at G. Okay, so that red point, that red point there is G. So here is G. So here is my center of mass. So the line CG is a vertical. Okay. Now the angle in question. So let's just try to give the rotation. If I actually rotate, how am I rotating? Excuse me. So if I'm rotating, we realize that you're falling down. Okay, and if you're falling down, no, we should have something. We should have something like this. All right, that's how we are rotating, like that. So we just have up. So this is my angle. So when we suspend, the rotation is kind of like this. Okay, so that's how the rotation is. Then the angle theta in question is the angle between the vertical, which is CG, the vertical is CG, and BC. So I need to put theta. So this is theta, alright? Here is theta. Now you realize that we can just form a right angle triangle, okay? Excuse me. So if I try to link, this is a horizontal distance, alright? It's perfectly horizontal. Okay, that is, this distance I'm drawing here is a distance from the center of mass to BC. Okay, that distance is a distance from the center of mass to BC. Now this distance here is a distance from the center of mass to DC. That's this vertical distance that I've just also indicated. So you see that we have a little right angle triangle. We have a little right angle triangle where we can now take tan theta. Alright, so if we try to take tan theta, let us see what we have. So let me first of all write down some things. so that you can try to copy. When the lamina is suspended freely at a point, let's say C, then the line joining the point of suspension, and the center of mass of the lamina is the vertical. Very important. Is a vertical. Okay, so with that said, in fact, here, let me just move everything downwards to the next page so we don't have to be moving up and down. Okay, so like we said, here is a little hint. All right, now the distance from G to BC is x bar. Okay, it's x bar. We found it already. So we have x bar, that's the distance. So this little guy here is just x bar. Okay, now you realize that if we take tan theta, just take tan theta, we need the tangent of the angle. What will be tan theta in this right angle triangle? It is opposite, which is x bar, over adjacent. Adjacent is this distance here. Okay, and we know that this distance here is the same as this distance, and this distance is y bar. Okay, this vertical distance here is y bar. So we are going to have tan theta to be equal to x bar divided by y bar. But we know that x bar and y bar are the same. Okay, so I can just have x bar divided by x bar, because x bar and y bar are the same. Alright, so at the end of the day, what do we have? We have 1. So we have proven that the tangent of the angle is equal to 1. Okay, so if you enjoyed the session, make sure you like, share, and you subscribe to the channel. I don't know how many minutes this is already, but I think it was a fruitful session with you guys. Stay blessed and see you guys in the next live session.